It's my pleasure to welcome Ivan. Ivan has been working on underwater systems for lobsters. And I found about his work because I was looking at some of the interesting underwater works which were published at Science Robotics. And your work got published, I think, in the last couple of months, I'm assuming. Um,
Yes.
and it's very fascinating because tracking and localizing these devices in the water is pretty challenging. It's like the GPS of which we all use outside of the water, and he's trying to bring that inside the oceans. Without further talking, let's actually welcome Ivan and listen to his fascinating work.
Okay, thank you. So, good morning, everybody. My name is Ivan Masmitjà. I'm a researcher at Universitat Politècnica de Catalunya in Barcelona, Spain. Recently, I finished my PhD studies in electronics engineering, where I was working in underwater target tracking using autonomous vehicles with Professor Spartacus Gomariz and Dr. Jacob Aguzzi. It's a pleasure to be here with you and sharing the work that we are conducting at UPC here in Barcelona. Consequently, I would like to thank the Professor Syam Golakota at the University of Washington, who invited me to give this talk. The purpose of this presentation is to share some thoughts about acoustic tracking, specifically for Norway lobsters and also other targets, using autonomous vehicles, which is mainly a joint effort between the UPC and also the Institut de Ciències del Mar, or ICM, in Barcelona. So I have divided this talk in 4 main sections. The first one, who we are, a short introduction of ourselves, then an introduction to the Norway Lobster project, which had the main goal to track these species at 400 meters deep, and also a short background in underwater target localization. Then I will explain some outcomes of the Norway Lobster campaign that we conducted last year, and finally, the future research lines that we are working on. So let's start. Who we are. I'm from SARTI Research Group, which is a research group from Electronics Engineering Department of the UPC. The UPC is a public polytechnical university in Catalonia, which is a region of Spain, in the northeast, where the capital is Barcelona. The UPC have different campuses spread across the territory, and SARTI is located mainly in the campus of Vilanova i la Geltrú, which is at 40 minutes south from Barcelona, more or less. And we are also in the new Diagonal Besòs campus in Barcelona. And here you can see the building, the new building. SARTI Research Group is part of the Electronical Engineering Department, as I said, and we are specialized in the scientific and technology development of equipment and systems for remote data acquisition and data treatment, where we have a strong background in development and underwater technology. We are a multidisciplinary team composed by professors, researchers, and PhD students from different disciplines. And also, I would like to emphasize that we have a strong collaboration with the Institut de Ciències del Mar, who are a biologist from the Spanish National Research Council, or CSIC. So the Institut de Ciències del Mar is the largest research institute of the CSIC dedicated to marine research, which conducts frontier research and fosters both knowledge and technology transfer on topics related to ocean and climate interactions, conservation, and sustainable use of marine life and ecosystems. So what we do, after this short introduction to ourselves, I would like to highlight some work that we have done during the last years related on underwater technology development. For example, we have developed and deployed 2 different buoys, one in front of each campus, in Vilanova i la Geltrú and in Barcelona. These buoys have solar panels, different ports to connect sensors, such as wind sensors, temperature measurements, conductivity, salinity, etc., and also communications to have in real time those measurements in our laboratories. For example, the buoy that is in Barcelona, that we can see a picture here on the right. was deployed in front of the Besòs River. This is an important river that crosses mainly high-density cities like Barcelona, with a lot of industries, and is used to monitorize the quality of its waters, both in situ, using a secondary node that you can see here in this map. We have a sensors just in the middle of the river, and also we have sensors in the buoy, which is placed here, just in front of the river in the sea. And the idea is to measure how the river changes the water of the Mediterranean Sea just in front of it, and measure the quality of this water. So this is a short video that I want to show you about the AUV that we have developed during the last years. This is an AUV called Gonai 2. This vehicle was designed to navigate in the surface, as you can see here in this picture. And when it's in the surface, it has the GPS signal, so it knows exactly its position. And at a specific localization, it makes a vertical drive profiles to sample the water column. And here, as I said, we can see the video doing a test that we conducted in front of Vilanova i la Geltrú Coast. During these years, we have had different PhD students who have worked in the mathematical model, control algorithms, electronics, the obstacle avoidance, etc. of this vehicle. So the vehicle right now has done a vertical dive, then looks for the next waypoint to reach and goes there. So this is a vehicle that we are currently working on. And also, to conclude this section, I would like to introduce the OPSI Underwater Observatory. This is maybe the most important project conducted till now. The OPSI is a cablet observatory at 4 kilometers of Vilanova i la Geltrú and placed at 20 meters deep. It's equipped with high-end technology instruments for underwater test and validation, and is part of the EMSO testing site, which is an European multidisciplinary seafloor and water column observatory system. And moreover, all the measurements are accessible through the EMUVNet portal in the European Marine Observatory and Data Network Initiative. Currently, the OPSI has been operative for more than 10 years, which is for us a huge milestone, as we are a small team compared to other much bigger organizations. Moreover, I would like to pinpoint that the OPSI is a unique platform of the Spanish Mediterranean coast. You can have access to the OPSI on the portal web, and we have a live camera recording what is going on underwater. You can see here the camera, 24 hours, 7 days per week. So with this instrument, we can take a lot of measurements and monitorize the life and the fauna and the quality of the waters in situ. Thanks to that, we have been participated in many national and European projects during the last year, such as the Nexus, Jericho, FIXOL3, ResNet, etc., and others. So after this short presentation of who we are and what we do, I will introduce the Norbert Lobster tracking project and also some background in the field of underwater target tracking, which is the main topic of this talk. So the project of tracking Norbert lobsters started inside the Spanish National Framework Program. The ICM won the ResNet project, where they wanted to study the movements of this species, which is one of the key living resources exploited in European waters. The main goal was to create accurate behavioral information to establish the size of marine protected areas and no-take zones. So here, the idea was to put those no-take zones in front of the Catalan coast. And we put this one no-take zone, and the idea was to monitorize the Norbert lobster in this area and study the behaviors. So we needed to know the movements of the Norbert lobsters. And thanks to this tight collaboration between the ICM and the UPC, as I explained previously, they contacted us to study the best way to track some target individuals. And we proposed two ways. One, by using moored receivers in a long basal line or LBL configuration, which is very common and is the most typical method. And two, we're using underwater vehicles as a virtual LBL. So the idea was to combine both methodologies in an innovative fashion. If we take a look on pros and cons of both methods, we have the following. From one hand, a static LBL gives us the highest accuracy, which is typically under meter resolution. However, the deployment cost is very high, especially at deeper waters, and the individuals can only be tracked in the deployment area. For example, if one of the species goes farther away from the receivers, we are not allowed to track and know its position. On the other hand, the use of underwater robots has the main advantage of their flexibility, quick deployment, and lower cost compared to many mooring lines, but with lower accuracy. Therefore, our initial idea was to use the main advantage of both methods, proposing a combination of them. So from one hand, we deployed the mooring lines, but also we did different transects with the vehicles in order to track some of the lobsters that go far away from the receivers, in order to improve and track those lobsters beyond the static moorings.
If I may ask you a question, can you explain as to why using underwater robots has a low accuracy?
I will explain that later on, but mainly due to the algorithms that we are using. Because with static receivers, we need to deploy at least 4 receivers. With the 4 receivers, we can compute the time difference of arrival, and then the algorithms that I will explain later on have a very good precision and accuracy. However, with a vehicle, we only have 1 vehicle. So it looks like that we only have 1 receiver, and the accuracy compared to 4 receivers is less due to the algorithm that we have to implement. I will explain later on some simulations and the results that we obtained. But before going further, we have to recap a little bit and start from the beginning to see these points. So before the ResNet project, I was working in my PhD at Monterey Bay Aquarium Research Institute, or MBARI, where I was using different algorithms to track underwater targets through autonomous vehicles and using acoustic modems. For example, I used a wave glider, you can see a picture here, to track a benthic rover at 4,000 meters depth in the Monterey Bay. Well, it was not exactly in the Monterey Bay, it was at 220 kilometers west of Central California coast, and the Monterey Bay is here. We also track this other instrument, which is a beam. And here you can see the Monterey Bay, and the MBARI is located just in the middle of the Monterey Bay. And this work was conducted together with Tom O'Reilly and Brian Keith from MBARI. Later on, when Dr. Joan Navarro and Dr. Joan Baptista from the ICM contacted us to work in the ResNet project to track the lobsters, we thought that the algorithm that I was working on could be modified to also track the target species. This hypothesis was tested at MBARI with the help of Dr. Kakani Katija, who was working on tracking jellyfishes. So the idea was great, but it's not as easy because we have to challenge a lot of difficulties. For example, the main limitation is the size, and therefore the performance of the acoustic tags that have to be used. Because till now I was using the acoustic modems, and the acoustic modems that I was using to track the benthic rover had two-way or bidirectional communication capabilities. That means that you can send information and also receive information from the device. And therefore, the distance between the target and the observer can be measured using the time of flight. Nonetheless, due to the size, the acoustic tags are simple transmitters. They transmit a ping periodically, for example, every minute. With this, you cannot measure the time of flight, and therefore, you cannot know the distance between the tag and the receiver. the range measurement is crucial in many algorithms to triangulate the target position. And this is why the algorithms are harder and the accuracy is lower than if we use acoustic modems or two-way communications. But of course, we cannot attach an acoustic modem, which is typically the size of a bottle of 1 liter or 1.5 liters, into a small normal lobster or a jellyfish. So we need to use these small acoustic tags, but with this limitation that I will show you how we overcome such limitations. So now if we focus in the tracking of acoustic tags using long baseline array systems, to solve these limitations of the bidirectional communication capabilities, the traditional methods such as LBL uses a set of different receivers. And instead of the range measurement, which will give you different circles, so when we have one receiver and we measure the range between the receiver and the target, we have a circle because we don't know if it's on the right or on the left, top or low, but it's inside of this circle. If you have different receivers, we have different circles of different ranges. So the intersection point is the position of the target. If we use acoustic tags, which don't give you the range, we can do something similar, but with a time difference of arrival. Instead of the range, we use the time difference of arrival of a ping signal generated by the acoustic tag and received by two different receivers. For example, the BS1 and the BS2, or the BS1 and the BS3. With the time difference of arrival, you can compute the target position by using the intersection point of different hyperbolas. So here we have hyperbolas instead of circles, which it is also called hyperbolic position systems. This is one of the methods used in the ResNet project that we was working and studying different algorithms, such as the particle filter or the weighted least square. Here, in this example, in this simulation, we can observe the performance of each method to track a target using 4 receivers and some results. So here we use these 4 receivers, and we studied the performance and the pros and cons of, for example, 4 different algorithms, such as the particle filter, the maximum a posteriori estimation, the weighted least square, and also the maximum likelihood. And we can see here that red crosses are the positions of the receivers, and the target that we want to follow was moving, doing this path. And all the algorithms could track and could know and estimate the position of the target. But some of the algorithms, for example, in this position on the top right corner, had some issues. For example, the green, which was the maximum likelihood. So looks like in this area, there's some kind of a dark spot where this algorithm had more difficulties to track the target. And this was due to the configuration of the array. If you change the configuration of the array, you put more receivers, you can solve this problem. But also, other algorithms works much better and the performance was better. So this kind of studies is what we did. Nonetheless, using this system, we have different independent receivers, as I explained it. And each one has its own clock and timestamp. And because usually the experiment can long many months, the clock drifts can be significant, which must be corrected before computing the position of each tag individual. Here we use a set of different steps to adjust this drift and synchronize the receiver's clocks using linear and polynomial regressions. For example, we can see that in our experiment, after 4 days, we had more than 2 seconds of drift. So only in 4 days. And 2 seconds of drift, if we take into account that the sound speed in water is 1.5 kilometers per second, means that in 2 seconds, we have 3 kilometers of error. So clearly, it's too much. We need to correct those drifts. After the correction, which is the right plot, we can observe that the error was less than 2 milliseconds during all the deployment, which was more than 3 months in this case, between June, July, up till September, October. This error is much better and it's close to the resolution of the receivers, which are 1 millisecond. The clocks of each receiver has this resolution of 1 millisecond, and here you can see that the error was lower than 2 milliseconds, which is quite good. And also we had some outliers that we had to filter later on. Then, after we have the receiver's clock synchronized, and before the computing the position of each tag, we need to adjust the localization of each receiver themselves. This maybe is not important in shallow waters, but at deeper depths, this is crucial, where you don't have access to the GPS signal, to the huge attenuation that electromagnetic waves suffer in water. That's why we are talking here, and everybody talks for acoustic underwater localization or acoustic modems, because we cannot use electromagnetic waves and we cannot use the Wi-Fi or the mobile phones, GPS. None of this technology works due to this attenuation that the electromagnetic wave suffers in water. And for example, here we can see that there's blue crosses at the initial deployment position of each receiver obtained with the research vessel GPS at the moment of its deployment. And we also deploy it on an acoustic tag here in the center of the receiver's array as a checkpoint to measure the performance of the algorithms and check that everything was working correctly. Then, with the algorithms that I studied, I computed the position of both the receivers and the central point. And I obtained that the central point was not where we thought at the beginning. Instead, we're located more to the right. So we measured this strange at the beginning behavior. Later on, we went to the localization with an ROV, a remote operated vehicle. And we observed that our calculations were great. And due to the currents and the depth, the real position of each receiver were different. During the deployment, the position, the initial deployment position and the final deployment position, when the receiver touched the seabed during this 400 meters deep of dive, suffers a strong deviation. And this was measured by the USBL, the ultra-short baseline position system that the ROV have. So we go there with the robots and we could observe exactly the true position of the final deployment of the receivers. And we observe here in the central point, which was the first indicator that we observed that something was strange, that the position computed with the algorithms, the time difference of arrival algorithms, and the position obtained with the robot were very close and far away from the initial thought obtained with the GPS of the research vessel. With this, our algorithms could be validated. So now if we focus on how we track acoustic tags using the vehicles, we have to remember that the information that we have here is very poor, and I will explain that. When we receive a ping, we only know that the target is nearby, but we don't have information about if the target is very close to us or very far away. Neither we don't know if the target is on the right or on the left, because we don't have any kind of information about the bearing or the range. However, what we know is that the acoustic power signal is small in those devices and can only be detected at 300 meters at most, typically. Other, depending on the manufacturer, can be longer or shorter. But let's say that it's 300 meters. Therefore, with this information, we can use the particle filter algorithm to spread a bunch of particles around us, which is our initial estimation. So our initial estimation when we receive the first ping from the tag is this one, this area, painted in blue. We don't know exactly if it's very close to our vehicle or far away, but it's at least at 300 meters from us. Then, as we move around, we can detect more pings, which can be used to update the weights of each particle in the particle filters, and finally fine-tune our initial estimation in order to get a better estimation of each position. So the idea is that the vehicle keeps doing circumferences or a circle-like path around the target in order to receive those pings and fine-tune and estimate better the position of the target.
Actually, I have a question, if you don't mind.
Yeah, sure.
About the particle filter. So when the signal was first detected, is there any like guideline for like which direction you are moving the vehicle to? Because I mean, at first I'm assuming like the particle filter is still pretty converged, so or it's just like a random to see like which direction move.
Yeah, I don't use the movement of the vehicle as an input to update the weights of the particle filter. So the particle filter are spread randomly, and each particle have as a state x, y position, and also estimation of the velocity of the target, but don't have any information about the vehicle orientation or position.
All right, thank you.
You're welcome. So here we can see the performance of this method in a simulation, where the AUV is indicated with this gray triangle, which is doing the circumferences over the target, which is the black arrow, and the particles are the red dots. Our target estimation is the red triangle. We can see that over time the particle converges over the true target position, and the AUV is able to track and follow the target. When the target makes this suddenly right turn, the algorithm needs some time to converge, but at the end it converges again, and the vehicle is able to know the position or have a good estimation of the position of the target and follow the target based on its estimation. And also here I would like to say that I used the detection of the pings to update the particle weights, but also which is represented in these darker stars, but also I use it when we don't receive any ping. So we know that the ping interval time is, let's say, 2 minutes. So if I'm in a position and after 5-10 minutes I don't receive any ping, I can assume that in this area is not likely that the target is here. So I use that also as information to update the weight of the particles. So if I have some particles here, I will put a very low weight in those particles. So this is the performance of the algorithm in simulations. Then we tested this method both here in Barcelona at OPSI and also at ENVARI. For example, at ENVARI, we were able to track a coastal profile float, which is this instrument that they was testing, and we take advantage of this experiment that they was conducting, and we installed a couple of acoustic tags. There we can see a picture here. These are from BEMCO, and we attached a couple of those tags here. And we used the WaveLider to track the coastal profile float. Here we can see the results of this experiment, where the error can be compared with other methods, such as the range-based methods. Of course, due to the poor information to feed the algorithm, the error using area only is greater than other methods. However, the target could be tracked, and this is very important because till now, we don't know any algorithm to do that. So if we have acoustic modems, you can implement a different methodology, different algorithms. And for example, here the blue The blue graph indicates the error over time. This is the position error, and this is the time of tracking the target using the range measurements and acoustic modems. So the error is very low. It's typically a few meters of error, 4, 5, at most 10 meters of error using the range. But if we don't have this information because the acoustic tags are very small and only transmit a signal periodically, so the information is very poor. But with the area only, which is the red color, the red plot, we can see that error is quite stable. That means that we are able to have an estimation and track more or less the target. The error is around 100 meters, which is big, but is much better than nothing. So that was, in that sense, a good result. So as a recap, we have seen that each method has its own limitations and benefits. From one side, the LBL, which is a static device that can only track the acoustic tags that are nearby. On the other hand, using vehicles which can not only know the position of the targets, but also can have the potentiality to follow the targets and go farther away. So this is why we propose a combination of both methods to track the Norway lobster at 400 meters depth, where we will see some results in the next section. So let's talk about some of the results of the Norway lobster experiment conducted inside of the ResNet project. So the ResNet project, the campaign consists of different oceanographic surveys. The first ones started on May-June of 2019 on board of the research vessel Garcia del Cid. We can see a picture here. After 106 days of collecting acoustic data, the receivers were recovered on September-October of 2019. In this case, we used the research vessel Sarmiento de Gamboa. And here we can see again a map of the area under study. So the procedure to catch, mark, and release the lobster can be observed in this slide. We used a cage to feed them, and we used zip ties and also glue to attach the tags on the top of the cephalothorax of the individuals, which were released using automatic canisters that we can see here. Those canisters had a door that opened when it reached the seafloor. That was very important. To release these animals had to be in the seafloor, not on the sea surface, because if not, during the dive, any predator or other animals could eat easily them. So we had to design these canisters. And also, in order to don't damage the eggs, because those animals usually live in a dark condition, because at 400 meters deep, the sunlight cannot reach. So we feed them during the night, and we use the red lights to protect the individuals. In addition, here we can see an interesting video obtained with an ROV, where we can see one of the Norway lobsters. So this is the typical seafloor of this area. And finally, one of the main results of our study is represented in this video, where we can see the movements of each target Norway lobster in its own habitat obtained during the experiment at 400 meters depth. In this the initial release point here can be seen clearly in the middle of the study area, and how the animals start to spread on the seafloor. Here, also the red crosses indicates the position of each receiver, and we can see all the movements during the days and night. The color changes accordingly to day and night. So we can see also if the animals were more active during the day or during the night, and if they go far away. For example, here we can see one of the Norway lobsters that go outside of the area under the study. Others stay more in the center of the relays point, etc. So with this kind of information, also here we can see more representation of the displacement, of the movements of each target individual. Also, with this information, the biologist can study the behavior of this species and determine the size of the protected area. Here represented in this square, green square. And that was the main goal, to see if the size of these protected areas are enough or not, or have to be bigger or less, and also how the species can recover in these protected areas. And finally, we can see also some transects conducted by both the AUV and also the ROV. During the surveys, we detected different tags. For example, in this picture, we can see the detection of 4 different individuals on the right of the receiver's array. So in this area, just on the right, we detected some of the individuals. So therefore, with this study, we identified the best procedures to localize both the acoustic receivers, but also the target lobsters, based on algorithms designed for off-the-shelf acoustic tags identification, using both fixed receiver and underwater vehicles. So the idea was to use commercial devices, acoustic tags from Brenco, also the receivers, etc. And these autonomous mobile platforms that deliver data on animal behavior beyond traditional fixed platforms capabilities represents an advance for prolonged and in situ monitoring of deep sea benthic animal behavior studies. And we want to implement them in a future project that I will explain a little bit about them in a few moments. So if you want, you can check our recent paper published in the Science Robotics with the title Mobile Robotic Platform for the Acoustic Tracking of Deep Sea Demersal Fishery Resources. And you can find free access through my personal webpage here indicated in this slide. So now to finish my talk, I just want to introduce to you some of the future research lines that we are working on. And specifically, I would like to highlight the main points of 3 projects. So the first one is related in the design of a new bidirectional acoustic tag. As I have explained to you, the main limitation of traditional acoustic tags is that they can only transmit acoustic signals, but cannot be used as receivers. Here, we want to overcome this limitation, and we are designing a bidirectional acoustic tag, or a miniaturized acoustic modem. With this new design, we will be able to measure the distance between the observer and the target, and this will boost traditional tracking methods. And here we can see some of the pictures and the initial prototypes that we are working on. A second project that we have presented this year, and we hope that will be funded, is to extend our previous studies in the ResNet project. In this case, the project BITER wants to study the interrelation among different protected areas spread across the Catalan coast. So not only one, instead a network of a no-take marine reserve. And specifically, we want to monitor 4 different areas, and not only the Norway lobsters, but also other key species such as the conger, the small spotted cat shark, or the hornet octopus. And in addition, we will test the potential effects of introducing structuring species such as the corals, like the cold water corals, to accelerate the recovery of these overfished habitats. To do this work, we have created a strong team by joining biologists, electronics engineers, and also robotic experts. In this project, we will work with Marc Carreras, for example, from the Universitat de Girona, who now is working in the design of the Girona 1000 AUV. With their help, we will fine-tune and improve the methods presented in these slides and implement them in an adaptive AUV. We will also develop a multiparametric augmented lander here. Both the adaptive AUV and the lander will be used as a low footprint and non-invasive technology methodologies to quantify the population and the ecological indicators to evaluate these high fishery impacted species and ecosystems. And finally, the third project that I want to present to you will start in a couple of months, and it's called Artificial Intelligence Methods for Underwater Tracking, or AI for U tracking. This project, funded by the European Commission in the prestigious Marie Curie Actions Individual Fellowship, and in this case as a global fellowship, this is a project that I want and I will allow me to investigate reinforcement learning methods to find the best trajectories of an AUV to track a specific object, where we also will investigate the multi-agent reinforcement learning techniques to use in a collaborative tracking procedures with different IUVs together. So here the idea is not only one IUV to follow and track a target animal, but using many vehicles together in order to improve the accuracy. And during this project, I will work with Kakani Katija at Enbari during 1+ year, and then 1 more year with Joan Navarro at ICM in Barcelona. So that's all what I wanted to share with you today. I hope that you enjoy it as much I enjoyed preparing this presentation, and maybe hopefully you will learn something. Anyway, if you want further information, please don't hesitate to contact me. Here you can see my email. You can also reach me by sending a DM on Twitter or whatever. And if some of you have interest to work with us or want to conduct some short stay in our laboratories here in Barcelona, we are open to receive candidates. We have different grant, scholarship opportunities, and it will be really a pleasure to work with you. So please take also this into account. That's all. Thank you very much.
Thank you so much, Ivan. That's a really, really good talk. We're going to open the floor for questions, and I can probably get the ball rolling a little bit. I have a question about your tiny tag, which you're designing as a future work. What is can you talk a little bit more about the range it can achieve? What is the power consumption? How long can it last? How frequently can it transmit, and all that good stuff?
Right now, we want to reach the same performance of a traditional acoustic tags, which is usually, as I said, the range is 300 meters, more or less. Also depend on the conditions of the sea, but let's say 300 meters deep. 300 meters range will be great. And expected lifetime, it depends of the ping period. So if you want to send a lot of pings, of course the life will be shorter than if you want only transmit, let's say, every 10 minutes. But it's around months, 1 month, 2 months, 3 months. But here the challenge is that we also want to receive information. So to receive acoustic information, we need to have an input stage, and input a signal conditioning unit, which have to be awake most of the time, which consumes a lot. So if we can reach 1 month, it will be great.
We have a couple of questions. Vikram, do you want to ask this question? Sorry.
Oh, yeah, sure. I was about to say, so the first question from Suvesha is, I was wondering how the tag was fitted onto the lobster, and is it required to do any kind of anesthesia?
No. Just we glue with glue and also some zip ties. But to protect this is quite robust species, and we only use these red lights to keep their vision, or to keep as most possible safe the animal.
My question was more from how do we really handle the lobsters, because their pincers can easily get in the way of us trying to put the tags on them.
Yeah, well, this is challenging. I'm an engineer, so I'm not used to do that. But ICM people, they have a lot of experience with animals, with Norway lobster. They have a lot of years of experience, and they know exactly how to have the animal hold the animal and attach things to them, etc. So it's something common, let's say that, for them.
Oh, okay. Thank you.
All right, we've got a lot more questions in the chat. If I'll just start going through these. If you guys want to ask the question yourself, feel free. But the next one is a clarification question about the circling. Does it need one robot, or does one robot follow one lobster at a time, or how does that work?
Yeah, well, that's also challenging because of course, if you want to follow more than one target, you can do that if the targets are more or less close to them. But if one of the targets go away, you cannot follow both. You have to decide which one you want to follow. So this is something that we are going to study in the next project, the Bitterroot project, with adaptive AUV. And we are going to implement algorithms to decide that in an upper layer. So they will decide which cluster, let's say cluster of tags they want to maintain and follow.
Okay. And so next question I see here is, can this be deployed in deep water where the depth drops off really quickly?
Sorry, can you repeat?
So I think the answer to that question is these are all on the seafloor, right?
Yes.
Yeah.
This is a benthic species, so it's always on the seafloor, and so you know exactly the depth and the Z position.
Another related question is, how does the terrain on the seafloor influence the accuracy?
Yes, in this case, the terrain was very flat, so you don't have any kind of issues in that aspect. But maybe in shallow waters, but for sure, that in shallow waters you have more problems in those kind of algorithms, because with the multipath, so you have a lot of echoes from the surface and also the sea bottom, and this multipath can introduce a lot of outliers and measurements that are not accurate. The range measurements or the time of flight or time difference of flight that are not accurate due to this multipath effect. But not here. Here at 400 meters deep, and the terrain was very flat, so we don't experience such kind of problems.
So another question is, so how long can these AUVs run?
Yes, it depends. For example, the experiments and the tests that I conducted at MBARI with the WaveLider. The WaveLider is an AUV that can run for months because it moves with the waves, so it don't need energy for its movement, and also have solar power that you can see here, so it can last months. So if you want to track acoustic tags or other instruments in a shallow waters or not as deep as 400 meters, you can use WaveLider for months. The other vehicles that we use like the Girona 500, it's around 4-6 hours.
Okay. So another question is, have you thought about using chirp pings instead of just a constant frequency ping?
What is the first one that you said?
So I think this is a question about the ping signal itself. Is it just a constant frequency, or does it send something like a chirp where it varies over time?
No, it's a constant frequency. Typically, all the manufacturers like Bemco, Sonotronics, they transmit at 69 kilohertz. And the modulation that they use is the PPM, the pulse position modulation. So usually they transmit 8 pulses. Each pulse is at 69 kilohertz and duration of 5 milliseconds. And the separation between these pulses indicates the tag ID, the indicator of the tag, or if it has some sensor, because some of the tags has a depth sensor, also transmit the information of the depth, using this PPM modulation, but the frequency is constant.
So I wanted to ask a question from Ivy. Is there a reason why you choose acoustic signals and not other types of signals in these experiments? Also, since all of these are happening underwater, are there any environmental factors that influence the quality of the signal itself?
Yes. We use the acoustic signals because it's the most common method to tag a species. They are a huge network of receivers deployed around the world that uses acoustic receivers and to detect the movements of target species. So a lot of researchers, a lot of biologists uses these acoustic tags to tag their species and their interest. And then with this network of receivers, they can know if the target is here in the Mediterranean Sea or goes to the Atlantic or whatever. So it's very, very common to use the acoustic signals in such kind of experiments. Of course, we could use optics. No? During the last years, there are this fashion in developing not an acoustic modem, but optics modem that uses the light to transmit information. But we didn't see any tag or a small device using optics. And also usually the optics range is a little bit less than the acoustic range. But we are moving at around a few hundred meters. So maybe the difference are quite equal here.
Are there, on a related question, like, are there any tags or techniques to get like kilometer ranges typically in underwater systems?
No, if you want to reach a kilometer distance in underwater is acoustics. Usually the electromagnetic wave underwater, you can have a range of centimeters, a couple of centimeters, 10 centimeters. Using light, you can reach 100, 200 meters. But if you want to reach 2, 3, 4, 5 kilometers, you need to use acoustics. And also you need to lower the frequency. So if you take a look on the market, the kind of acoustic modems that you can find, you will see that if you want a very high frequency acoustic modems with a wide range, it's not possible. If you want to have a long range, you need to lower the frequency.
I see. Benjamin had a question on, do you run the particle filter on board on the robot itself, or do you process the data offline on a more powerful computer because the state vector seems rather large for tracking the lobster?
Yes. During the experiments using ARIA only to track the lobster, all the algorithms were offline. So first we collected all the information and then offline with another computer, not the computer in the AUV, we run the different algorithms. But during the first experiment that I conducted at MBARI using the acoustic modems to localize the target in situ, we run also the particle filter in the WaveLider, because the WaveLider has different computers, and one of the computers is only for the navigation and you don't have access to it, but you have another computer where you can have access and implement your own code and algorithms.
I do want to add a question which Matthew and Ruby had, combine the two questions. How many lobsters did you actually track? And can you comment a little bit more on how does your system scale in terms of the number of tags and the UAVs required?
Yes, that is interesting. Here we tagged 33 Norway lobsters. And here one of the main challenges is the budget, because each tag is cost around 200-300 euros. So it's about $400. So are very expensive. And with the initial budget, we could only tag buy 33 tags to tag 33 species. But also, you cannot tag a lot of or infinite species in the same area, because you will have a lot of overlaps between the signal transmissions, and you will lose a lot of information. So if you want to tag a lot of lobsters in the same area, you need you need that the interval of transmission of each tag be increased. So you cannot transmit every minute. Instead, you need to transmit the position or the ping of each tag every half an hour, maybe, if you want to put a lot of tags in the same localization. Because if not, you have a lot of overlaps between the transmissions. And also, we use it here only one vehicle. So the main limitation using one vehicle is the area that you can cover, because as I said, you only have 4-6 hours of working. So you only have this time to make a dive and follow a path in order to detect some lobsters. Then you need to recover the vehicle, recharge the batteries, and deploy again. So if you have more vehicles, you can cover a wider area. So that will be interesting. And for the next project, the bitter one, we want to improve, and we want to increase the species that we are going to tag, and we want to tag 500 species. So we want to make a big jump here.
Is there a question?
I was wondering if the project Biter that was used, that you mentioned about, can it also be used for coral inspection or to control coral poaching and inspection, basically? That might probably require the use of cameras, but is it possible to kind of negate the use of cameras for?
Yes. Yes, that's an interesting question. And yes, we are going to implement also underwater cameras on the lander and also acoustic cameras on the AUV. So we will have both technologies, acoustic cameras. And the interesting part of the acoustic cameras is that we don't have to use the light, because with cameras, of course, at 400 meters depth, is everything dark, so we need to put lights, and with the lights we can disturb the behavior of the animals that we want to study. And with the acoustic cameras, that is a very nice technology, we don't need to use the light. So this will improve the study, and it's a thing that we will work, hopefully. And on the lander, we will use cameras, common video cameras, and we'll record in a time-lapse fashion pictures of the seafloor, and also we are going to implement different corals in front of the cameras in order to see the evolution of those corals during the months.
So building on that question, sorry, I had this question, I'm going to ask it. Are you going to store the camera data locally, or are you going to be, is there ways in which you can stream the data acoustically to another? Is it possible? Because camera data is very high bandwidth, right? Yeah, right. That's a problem. But the cameras that we are going to use are specialized cameras which have onboard processors in order to compress the information, the pictures, and also they are able to select parts of the picture that are interested. So they take different pictures over time, and maybe they can crop only the part of the picture that has not changed or that has changed, and only send this information. And yes, and this is also an interesting part of our project, the Biter project, that we want to use what is called vessel of opportunity. So we want to involve also the fishing vessels, the people that goes on the sea every day to fish and to make their lives. And we are going to rent and pay those fishermen to go there, and one day or during a couple of days, instead of doing their activity, they will deploy buoys
with acoustic modems. And with these ones, we will be able to download the information stored on the lander and have in quasi real time, every week or every few days, the information. So we can then change the study if we need to put more corals or we need to relocate the lander, etc.
I'm going to ask a couple of questions so that we get to all the questions. Alex and Astitwa had a question, which is, does salinity affect the acoustic communication range? And what about multipath? And you have rocks reflecting things, and is that a huge issue if the lobster goes into hiding areas and so on?
Yes, as I said before, in a shallow waters with maybe if you have a deep canyon, you have a lot of multipath. Here it's practically flat and you don't have these issues. What we have is that the lobsters, they make holes to put themselves inside, to protect from possible predators. So when the lobster is inside of the hole, we lose the signal because the acoustic signal suffers more attenuation and we cannot receive the signal. But that's also interesting because with that, we know the behavior of the lobsters and we can see how many, what hours of the day they are outside of the hole, maybe hunting or eating, or they are inside of the hole. Because if we receive pings periodically, we know that they are outside. And if we don't receive any ping during many hours, it's because they are inside. So we can make also studies in behavioral.
Cool. Jiarong had a question, which I think I also had. You mentioned that the AUV approach has a low accuracy because it uses only one observation point, which is a robot. There has been work in the radar and the Wi-Fi community, for example, where it's like similar to the synthetic aperture radar, where you have a radar on the airplane and it's actually moving. You can simulate multiple antennas, and that gives you the range resolution to basically get better imaging or Wi-Fi localization. Have people explored those kind of approaches where just using a single robot, but because the robot is actually moving and you know the trajectory of the robot, you basically create a synthetic aperture sonar, which you can use to then get a better resolution?
Yes, right. Yeah, yes. And this is more or less what we have done here. With our range-based algorithms, we have a vehicle that we know the position of the vehicle. So we move the vehicle at different points, we measure the range, and then with these measurements, we simulate a virtual LBL. So we simulate like we had, let's say, 10 receivers at 10 different positions, but we don't have 10 receivers. We only have one receiver that is moving. So yes, we applied such kind of approximations. But here the problem is that we cannot measure the range. We only have the detection of a ping, but we don't know if the ping is very close to us, far away, on the right, on the left. So the information that we have using acoustic tags is very limited. And that's why we have bigger errors in this case.
So Kyle had a question, which is, what level of locomotion control do you need for the AUV? And in particular, if you want to make the AUVs cheaper, smaller, and low power in nature, where do you see the limitations? Are they mechanical, electrical, computing? Where exactly are the limitations to make them cheap and low power and last for a long time?
Yes. Well, there are some AUVs because the main power consumption is to move the vehicle. So if you need thrusters to move the vehicle, the consumption of those thrusters are very high. So you need huge batteries. However, maybe you don't need to move the vehicle during all the way. No, you can have what it's called a glider, which is basically a vehicle that goes up and down very slowly, or it just drift with the currents. So you don't need to turn on the thruster continuously to move the vehicles. That's one point. And also to lower the cost, it's difficult because the underwater is a very hard environment. If you want to work in a very big depths, you need stainless steel cylinders, waterproof cylinders. All the technology to make the vehicles waterproof is very expensive. You can buy some cheap devices, but it's hard.
So I'm going to combine some of the questions here. Shao, Laurel, and Benjamin had a question about, first, why are you tracking lobsters? What's special about them? And second, what is the unique thing you learned about their movement patterns from this project?
Yes, for the lobster here is important because it is a very important species in all Europe. So a lot of people, a lot of industry is around this species because it is a very good species to eat, and the people pay a lot of money for those species. And that's why, no? I think that I'm not an expert here, so I'm a technician. My colleagues, the biologists, they will explain better this thing. But it's one of the key species in Europe because as a quantity and as a value, as a quantity of money that they move during the year. So that's why we choose this species. And here in the Catalan coast specifically is a very important for all the fisheries around the Catalan coast. That's why. And we want to study the behavior, no, the movements, because it's a overexploited species. So each year the fisheries catch less and less and less. So we need to do something, because if we don't do anything, this species will disappear from the Catalan coast, and all the industry around will also disappear. So that's a problem that we need to solve now in order to preserve the future of this species and all the industry around.
Professor, I had a question, actually an idea specifically.
Go ahead.
So I thought that, I mean, in the AUV itself, can we load sensors and like when it's near the targets, it can launch itself, and like concept of swarm drones, and then track lobsters. I think that can solve some of the problems of not having static LBL.
I'm not sure if I heard you correctly, but you propose to deploy the receivers using the AUV?
Yes. In the AUV itself, there is a compartment where you just open it, and then in the sea itself, those sensors or small devices get launched, and they autonomously also track the lobsters. And
yes.
I mean, yes.
Small devices. Yeah, that will be great, no?
So we can actually do something like we can tie it by rope. I mean, I'm just thinking extempore. We can tie it by rope, all these sensors or maybe small objects, and then launch it in underwater. And I mean, after that, when the experiment is done, we can just recall it back.
Yeah, this is something that is done with a ROV, but the problem in the perspective of a budget is that to operate an ROV, you need a big research vessel with a lot of crew on board. It's very expensive. You need the ROV. So that's cost 100,000 euros per hour. So that's very expensive. If we can go just with a small fishing boat and an AUV, that will reduce a lot the overall cost. And of course,
I mean, can it? I mean, it's not really part of the research project, but I think these devices can also be used to find resource-rich and I mean, where resource-rich areas in underwater where more fishes and everything are there. I think that is some data that is very commercially useful for fishermen and probably for governments also. So maybe in that way it can be useful for your project.
Yeah, sure. No, what you propose sounds really interesting, no? To deploy the receivers with vehicles, and if you can do that automatically without any kind of human intervention, that will be great. And also, what will be even greater is you can deploy the receivers, and if you see that the lobster goes or the species that you want to track goes to another area, take those receivers and move also the receivers to another area. That would be great.
That's true. There are multiple variations.
So I wanted we have 5 more minutes. I want to combine a couple of questions which were asked by Ethan, Ton, and Alex, which is, what are the potential, I mean, you're putting sensors on these things, they can get eaten up. What are the environmental issues with that? And also, does that affect the animal itself in any way, because they're carrying it and the sound is being generated? Are there other sounds which interfere with what's happening?
Yes. Again, here I'm not a biologist. I don't have a lot of information. I cannot explain to you a lot of things about that. But ICM, the biologist from Barcelona, they have conducted a lot of research in these animals, a lot of research in laboratories. So they know exactly the behavior of these species. And in the laboratories, they have tracked in water tanks the movement of lobsters using cameras and also attaching tags and devices on them. And they found that the problems that the lobster can suffer is not very important. That from one side. And then if this kind of acoustic tags can be an issue for the environment of the animal eat the tag, I don't know the answer exactly. But as I said, this is a very common procedure. So a lot of people is doing that, and I suppose that they are safe.
So one last question before we let you go. We have a lot of questions.
That's great.
Is something Anurag and a couple of other people asked. You've been using, I'm going to make it a little bit more general than what they asked, but you've been using this custom tags, and you talked about creating your own tags, but how many people actually do create their own tags? For example, you could create directionality for your tags. Maybe that'll help. Maybe you can send chirps. We have all these different things which you could do to, if you make it software programmable, where you can transmit your own signals, receive your own signals, like software defined radios, that can really, really help with innovation in underwater systems. So what are your thoughts on the research happening there versus just using tags which commercial companies are selling you?
Yeah, the idea of developing our own tags is because, as you said, we are going to have more flexibility to implement our own signals, our own frequencies, etc. And for example, what we want to do is we are in touch with an acoustic modem company in Germany, here in Europe, who are very specialized in underwater acoustic modems, and also USBL. That USBL is an ultra short baseline system, which is a kind of a LBL, but all the antennas are together. So in one instrument, you can obtain the range measurement and also the bearing, the angle direction of the acoustic modem. And we want to use their receivers to detect our tags. So they have these software-defined modems that we can modify the firmware of their devices in order to be able to detect our own devices. So the idea is to make this collaboration between the industry and ourselves. But this flexibility it's very important for us. And also, we are in touch with the European Tracking Network, that is an association of in a European framework, that they want to standardize the acoustic model, the acoustic tags. So until now, we have different manufacturers. Each manufacturer have its own protocols, their own signal frequencies, and sometimes it's difficult. And what they want, the goal that they try to find to achieve is any kind of tags from any kind of manufacturer can be listened from any receiver from any manufacturer. So this interrelation between manufacturers. This will be great. And also we are interested on that, and we want to make our own tag readable, no, for other receivers.
Perfect. This has been great. I think we had so much interest in your talk. I think we're running out of time now, but thank you so much, Ivan, again, for taking the time to give a presentation here. And hopefully we can reach out to you and have some collaborations.
Yes, anytime. That is great. It has been a nice day.